Good morning, all. The topic of my poster is Cybersecurity of Multi-Agent System, Passivity-based Attack Identification and Mitigation. Let's start. Let's go through the introduction and challenges. So, some safety concerns of multi-agent systems can be divided into two parts, which is physical and cyber threats. In physical threats, we have some fault estimation and other thing related to fault of the system, like some physical problem might be there on the systems. And then we have cyber threats. So these cyber threats are actually intentionally done by the uh, external adversary, whereas physical threats can be just some case of mishappening with the system, or it can be a physical threat by the external adversary as well. But cyber threats are generally only caused by the external adversary, so they are of main concern. And further, these things can be divided into homogeneous multi-agent system and heterogeneous multi-agent system. So homogeneous multi-agent system will means that all the agents will have similar dynamics, and heterogeneous means that or all of the agents may have different dynamics than the other agents. So challenges in security of cyber physical system is this, that because of more number of parts in the system, and there's a higher heterogeneity of the system, more points of attack are available to the attacker. Then there is one problem that the signature based intrusion detection cannot be used in cyber physical system because they already have limited computational power and memory. So saving up signatures of different users is not always possible. Also, giving software updates is not possible in case of cyber physical system. Like if a power plant is running, we cannot just stop the power plant to update some software, unlike our phone and laptops. And cyber physical systems are generally designed to be autonomous, such that minimum human interaction is required, and thus they need to be resilient to any external attack. And as we already discussed, that continuous operation is required uh, even under malicious attack. We cannot shut down a physical system just to prevent some attack. So these are some recent large scale incidences related to cyber security of physical systems. So you can read this. So now let's come to our approach. So our approach is based on detection and switching of control. So we are using this attack detections because it gives us a signal. So that signal can be used for generating an alarm for human interference, so that any human or intelligent body can take care of the attack. And eh, we can even start some other communication protocols or algorithms to remove the attacker from the system. For example, we can switch our communication channel so that the on the other channel the attacker may not be present, so we can avoid attack in that case as well. And then also we can just switch our controller to mitigate whatever the attack is there. And another benefit of this attack detection is that in case we can sacrifice a few of the agents, so we can isolate those compromised agents from our system, and remaining agents can achieve their goal. And benefits of switching controller are as below. So switching control reduces computational requirement when we are not under attack. So it, because it will not be estimating the value, what the value of the attack is, where the attack is, and other things. And another benefit of switching control is that it gives better performance in some linear cases. So reference for that is given. If you are interested, you can read. So let's come to our problem. And before that, let's come to the preliminaries. So first we are using concept of passivity for attack detection. So let's know what passivity is. So as can be seen in this figure, a resistor is a most basic passive element in circuit theory. So it does not generate any energy of its own. It can only dissipate the energy present in the system. So here we can see that if this input is positive, the output is positive. If input is negative, the output is negative. So that generally means that whatever the input or output may be, the product of input and output will always be positive. So we can see that if we multiply u times y here, it will be a positive uh, product, and here as well it will be a positive product. So this is in case of linear systems, or we can say scalar systems. But in case of non-scalar systems, which are having multiple inputs and outputs, this relation can be presented by this U transpose Y. So for a passive system, U transpose Y will always be greater than or equal to 0. But if in some cases it is equal to 0, then the system is non-dissipative and it is called as lossless. And in some cases it can be that the system satisfies this condition only, so there is no equal to sign here. In that case, the system is known to have excess of passivity. So the graph for this case is given here. So we studied about passivity of a statical system just now, but what in case of dynamical system? Because in dynamical system we might have some storage value that the system is storing some energy. So that energy storage is given by this variable s in this equation, and the condition changes from u transpose y greater than equal to 0 to u transpose y greater than equal to s dot. That is, this energy supplied to the system is always greater than or equal to change in stored energy of the system. If change in stored energy is equal to energy supplied to the system, then the system is called lossless. And if this condition satisfies that this equal to sign is not there and only u transpose y is greater than s dot, then we can say the system has excess of passivity. So we can detect whether a system is passive or not by this schematic diagram. So we will just take this input u and y, multiply them as given here, u transpose y. So for that we need to make sure that u and y are of same dimensions so that this product exists, and we can define our storage value, storage function, calculate that and compare if this condition is being satisfied or not. If this condition is satisfied, we can declare that the system is passive. If this condition is not satisfied, we can declare that the system is non-passive. So let's come to our problem. So we are considering a linear system, linear agents, and there are a total of n number of agents with these dynamics that we can see here, and some basic assumptions are considered that the system, each agent is controllable and each agent is observable. So now we have this standard result about consensus of passive system. So given a passive system with this dynamics where y is output, u is input, given this control input of in equation 4, so this system can achieve consensus under a strongly connected topology, and one such example is given here in this figure where some single integrator passive agents are achieving consensus under this control law. So now our attack model. So we have considered this attack model that whatever input that a controller generates does not reach exactly to the plant. Some addition by the attacker might be there in the control input, and this compromised input reaches to the plant. We do not consider any attack on this output side of the system, and even if there might have been an attack on the output side, we could have just used some observer to estimate the state of the system. So this intrusion detector is there to detect any attack on the system, which will be considered in coming slides. So Instead of U, the control input that reaches the plant will be UC, which is given by this equation 5, and our updated agent model will become this. So this U gets replaced by U. Some basic assumptions are there on the attack signal, that it is a Lipschitz, that is, it is bounded and its derivative is also bounded. So for attack detection we have these results. So given this matrix M, uh, and if this matrix is positive definite, then we have that the system is passive. But if there is any attack on the system, as seen from point P and Q, the controller may not think that the system is behaving as a passive system based on what the attack UA is, and we get this condition. So if this condition is violated by this attack signal UA, then we can say that the system is not behaving as a passive system, and we can declare that we are under attack. And if this condition is not violated, the system behaves as a passive system, and even though it might be under attack, it will achieve consensus because of its passivity. So once we detect that the system is under attack, we need to mitigate it. So we have a switching controller, which is given by this equation. So schematic diagram of the controller is given here. So we have this normal operation and defense mode of the controller. In normal operation we have the consensus algorithm, which was given by equation 4. It is just written in this matrix form here, and as soon as we detect that some condition is this condition is satisfied, the system is not behaving as a passive system, we set delta is equal to 1 and switch to our defense mode. After switching to defense mode, we keep checking whether the system is again behaving as a passive system or not. If it is behaving as a passive system, we wait for a while and keep checking it for a while, for some time, and based on what the count is, if this count reaches above this threshold value, then we declare that yes, the attack has ended, and we switch back to normal mode. But if in between we get any condition that yes, the system is still behaving as a non-passive system, we still remain in the defense mode. So here in the switching controller we are adding some term along with this normal operation control. So this term is given by this equation here, so which is an estimate of the attack signal on the agent, where this B dagger is just pseudo inverse of matrix B. It is also known as Moore-Penrose inverse of matrix B. So now we have some simulation results to show. So first let's go through the data that we have used for our simulation. So we have used this matrix A, we have used the total 5 number of agents, this matrix B and C. So these matrices satisfy our assumption that the system is passive, controllable and observable. Then we have this Laplacian matrix of topology, for which the graph is given here. So this satisfies that the topology is strongly connected. Then we have some initial conditions, this attack signal values and time of attack from 2 seconds to 5 seconds. So first we are checking whether the system is behaving as a passive system or not. For that we have this thing. So red line is our change in stored energy and yellow line is our input energy. So we can see that U transpose Y is greater than S dot for from starting to 2 seconds where the attack starts. As soon as the attack starts, this system shows non-passivity, so we switch our controller at time 2. So this is the estimated attack signal in red color, and in blue color we have actual attack signal. Here we can see that a little bit of delay is there for detecting this non-passivity of the system, but as soon as this condition is detected, the estimator starts working and almost accurately estimates the attack signal on the system. Uh, as per the output of the system, we have all three states for a third order system. So for first state, we can see that the states are synchronizing perfectly, and in the zoomed part we can see that from time t is equal to 2 to 5, about t equal to 5, some oscillations are seen in the system, which is because of the attack, but these oscillations are very less and bounded. And again for the second state we see a similar pattern, that some little bit of oscillations are there during the attack time, but which are bounded and very less. And same for the third state of the agents. So they are achieving consensus with a little bit of oscillations during the attack time, but they remain bounded, and as soon as the attack ends, it is perfectly achieving consensus. So that's all. Thank you.